Okay, students. So good morning. Only 4 of you. Okay. So we'll be starting with the new topic today now. We'll be starting with the next one. So thermal properties of material. Okay. Okay. So 5 of you, yeah. Okay, good. So let's start. Okay. Okay, students, can you hear me?
Yes.
Can see the slide there?
Yes.
Okay, good. Okay, so today we learn about ideal gas. Before ideal gas, we learn about thermometer. Okay, so the thermometer, ideal gas, and thermometric property. This like under temperature, about heat. The heat energy. In exam, you can expect it. You can expect like 2 questions come out from these 3 topics. Okay. So ideal gas can be a lone ranger. The thermal property can be together with temperature. Okay. Okay, you see this topic. You see the subtopic here listed here. Is it all familiar for you? The first one is familiar for you, right? You heard of specific capacity. You heard of specific latent heat, I believe.
Yes.
You heard of internal energy?
I think not directly.
Not really in depth. So you never, not really in depth, you learned about internal energy last time. And of course, you never learned about first law of thermodynamics. So this topic, the first 2 is something you learned before. The last 2 is something new. Okay. So that's about this topic. It's a specific capacity. Okay. So let's proceed. Okay, this is the learning outcome. We go to the questions. First, as usual, you need to know how solid, liquid, and gas, how the atoms are arranged, how they move, do they vibrate or they move randomly, and so on. This you learned before in early studies. So first we go for solid. Solid, this is how it's going to looks like. Imagination. They has a regular geometrical structure. The atoms or molecules are, of course, closely packed. Okay, they are closely packed. So therefore, they have a high density. Okay, they are very closely packed. Okay, of course, they have a fixed volume and fixed shape. Fixed volume, fixed shape, and of course, return to original length after the force is removed normally. And they only experience what? Vibration. They only vibrate about a fixed point. Okay, and the atomic intermolecular force is said to be 3 times 10 to the power negative 10. Okay, negative 10. Yeah, this is the intermolecular distance spacing. Okay. Liquid. Okay, liquid expected. This is how it should move. The particles are freely move, but they move layer by layer. Okay, the molecules are slightly further apart, of course, slightly further apart than in solid, but still not much of a difference. Okay, in A levels, the spacing ratio. What is the spacing ratio between solid, liquid, and gas? 1, 1, 10. Let's remember. The spacing between solid and liquid still 1, 1. So that means not much of a difference. So solid, liquid, we conclude that there is not much of a difference in the spacing. Still consider as 1, 1. 1, 1 ratio. Okay. So still as a high density. Okay, they occur in a cluster and the molecule can move between them. Okay, they can move between them. They move like a cluster, in a cluster. Fixed volume, of course, not fixed shape. They don't have fixed shape. Okay. So again, almost incompressible, like solid. Okay, almost incompressible. The only difference between solid and liquid, I think you don't have a fixed shape. They don't have a fixed shape. Other than that, it's similar. Okay. The order of separation of the molecule liquid is about the same as that of solid. These liquids. So they can ask how the particles are arranged in liquids and how the intermolecular force looks like. So these are the descriptions you have to write. Then finally, gas. Okay, gas is totally different from the solid and liquid. No fixed volume, no fixed shape. The molecules are very far apart. Has a very low density. Very low density. No fixed volume, no fixed shape. Gas fill up the entire space. They are easily compressible. Okay, all are opposite to liquid and solid. Okay, and at the standard temperature and pressure, the average separation of the molecule is about 33 times 10 power negative 10. Remember the ratio 1, 10. So the ratio of gas is found to be spacing found to be 10 times more further than the solid and liquid, and it moves randomly. Okay, they move randomly. Okay, so these three you learned before. You learned before. Just remember as fact. Remember. Okay, the description just now we discussed is in this table. Okay, structure of characteristic movement of molecules all here. Okay, so regular shape, regular structure. So the size, everything's here. You need to memorize it. Okay, movement, solid only vibrate. Okay, and liquid move layer by layer. Okay, and gas we can say it's a random movement, random motion at high speed. Okay. Okay. So now we're going to move on to heat capacity. Okay. You have specific heat capacity. You heard of heat capacity. Heat capacity is different from specific heat capacity. Okay. What is heat capacity? The amount of heat required to rise the temperature of a substance by 1 Kelvin or 1 degree Celsius. It's called specific heat capacity. Okay. Formula is what? Q is the energy. So Q equals to C changes in theta. This capacity, this is called heat capacity. Okay, capital C. You heard specific heat capacity, the one that's quite common. Q equals to MC theta. MC changes in temperature theta. This calls specific heat capacity. This is small c. On the left, on the right is small c. This is heat capacity. How heat capacity connected to specific capacity? M times C. M times T, mass times specific capacity is your heat capacity. Okay. Mass times specific capacity is your heat capacity. Okay. So yeah. So heat capacity, the unit is joule per Kelvin. Okay, joule per Kelvin. Let's say you have a kettle, aluminium kettle. You have aluminium kettle made of 2 kilogram. Okay, 2 kilogram. Okay. The aluminium will have a specific capacity, let's say is 2000. So let's say 2000. Specific capacity, 2000. So 2000, what is the unit for specific capacity? Anybody? Specific capacity? Joule per kg per Kelvin. Per Kelvin. Joule per kg per Kelvin. So specific capacity of the aluminium, let's say I give you 2000. These 2 kilogram of kettle will have heat capacity of how much? Heat capacity of this aluminium how much? So what is heat capacity? The capital C is same as mass times specific heat capacity. So the mass is 2 kilogram. Specific capacity is 2000. So the heat capacity is 4000 joule per Kelvin. Okay. Okay. So in reality, heat capacity very low profile. Can you survive with specific capacity? Yes, of course, you can survive with specific capacity. But in A-level syllabus, they want you to know heat capacity too. Okay, heat capacity for one cattle 2 kilogram, another cattle let's say is 4 kilogram. 2 kilogram cattle, 4 kilogram cattle. Both will have different specific, different heat capacity, but both will have the same specific heat capacity if they made of same material. If they made of same material, they will have the same specific capacity, but heat capacity might differ. Big mass will have a big heat capacity. Okay. Any questions from here? No problem. Okay, so now this graph I feel also quite familiar for you. Temperature with energy input. Okay, and energy is input. A solid from A to B, the substance will be in form of solid. Okay, the energy absorbed we can calculate by using MC theta or C theta if you want. Then B is start to melt, phase change happen. It will form in form of what? Solid and liquid mixture. Then at the end, all become liquid, goes up, so it's MC theta again. So D to E, liquid plus gas, then finally become gas. Okay. So when the temperature rises from AB, CD, and EF, we use MC theta to calculate the energy absorbed. And phase change happen, we use another type of energy. What is that? Latent of fusion and vaporization we use, correct? We use latent of fusion and vaporization. Okay. We will come back to that later. Okay. Okay, so next, specific heat capacity. So C, the small c, this is more important term to remember. What is specific capacity? The amount of heat energy required to rise the temperature of a unit mass of substance by 1 Kelvin. Okay, 1 Kelvin. Better you say 1 Kelvin instead of 1 degree Celsius, because Kelvin is a SI unit. Okay, so Q equals to MC theta, joule per kilogram per Kelvin. Okay. Okay. So, okay, now the question is, when the solid liquid gas change phase, melting and boiling, during melting and boiling, phase change happens. Why is there is no change in temperature when melting and boiling is taking place? Okay, you know this answer, I think, believe in O levels or SPM. Okay, why during melting there is no temperature change? Anybody?
The energy is used to overcome the intermolecular force
Yes.
between the molecules.
Yeah, the energy is used to overcome the intermolecular force. So, or to break the bond, or to overcome the intermolecular force. Okay, so therefore the temperature never rises. Okay, DE, during vaporization, why temperature never rises? Anyone? Also to break the intermolecular force further. Plus, what else? Break the intermolecular force.
Atmospheric pressure.
Yeah, again.
The atmospheric pressure.
Atmospheric pressure, to do work against atmospheric pressure due to expansion. Due to expansion, to do work, to do work against atmospheric pressure. Okay. So vaporization greater or latent heat greater? Latent heat of fusion greater or latent heat of vaporization greater for a substance? Vaporization greater or fusion greater for a substance? Normally, vaporization is greater. Normally, vaporization is greater than the latent heat of fusion. Why? The reason just now, because vaporization not only to use to break the bond, but to do work, during expansion. okay, to do work against atmospheric pressure during expansion. So vaporization is always far bigger than the fusion. Okay. So during melting, when melting, the heat supplied is used to break progressively the bond between the molecules. Orderly structure breaks down disordered phase. Intermolecular distance do not increase significantly. Yeah. So the bond breaks, but the intermolecular force does not increase significantly. Not much of a big difference line in intermolecular force. As I said, the ratio of solid liquid spacing still 1:1. Okay. So no change in the average molecular kinetic energy. Yeah, kinetic energy of the molecule also doesn't change. Okay. Anyone? Why kinetic energy of the molecules doesn't change? Because kinetic energy of molecules is proportional to what? Anyone? You
Oh,
learned last topic?
when
Temperature.
which is
Temperature, right?
it's
Yes, temperature. The kinetic energy is proportional to temperature. So B to C, because temperature never rise, the kinetic energy never change. Okay? Yeah. So
oh,
that's during change phase.
so we say intermolecular force or the bonds, quote unquote.
Both accepted. Both accepted intermolecular force. Break progressively bonds between the molecules. So you can say to 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 do work against to overcome the intermolecular force also accepted. Okay. So EK proportional to temperature. EK proportional to temperature. So no rise in kinetic energy. Okay. So yeah, A to B, EK increases. B to C, no change in EK. C to D, EK increases further. So when temperature rises, EK of the particle rises. So this is melting. So for the case of boiling, uh, boiling part, to overcome the intermolecular force of attraction, the rest of heat supplied is used to do external work in pushing back the surrounding atmosphere, or to do work against atmospheric pressure during expansion. Okay, so work need to be done to do work against atmospheric pressure during expansion. So therefore, no heat supplied is used to change the average molecular kinetic energy. There's no change in temperature. Okay, so that's boiling. Why temperature never rises. Okay, so the heat supplied during solid, liquid, and latent is called latent of fusion. Okay, during during change from liquid to vapor, we call latent of vaporization. Okay, so definition of latent of fusion. Latent of fusion, yeah, the amount of heat energy required to change a unit mass of substance from solid to liquid state without change in temperature. Most of the students sometimes they missed out the last wording. Without change in temperature. You must say without change in temperature. Okay, that is latent of fusion. The amount of heat energy required to change phase per unit mass of substance from solid to liquid without change in temperature. Okay, so latent of fusion. You know this before. So latent of vaporization, LV, same wording, just liquid to vapor. Okay, the amount of heat energy required to change a unit mass of substance from liquid to vapor without change in temperature. Okay, specific latent of vaporization. Next, what is the difference between fusion and vaporization? As I said, for the same substance, which will be greater? Of course, vaporization is greater. So LV always greater than the LF. I told you the reason. LF only to break the molecular bonds, but LV to overcome the intermolecular attraction, and work done to push back the atmosphere. So Latent heat of vaporization always greater than the latent heat of fusion. Okay. So this is some values for latent heat of fusion and vaporization. You can see each substance, like ammonia for water. Where's water? Water, the latent heat of fusion is 334, but vaporization is like 2260. So how many times greater? Around six times greater, 6 to 7 times. The vaporization is greater than the fusion. So a lot of energy is used to do work against atmospheric expansion. Okay. So these values you don't need to remember, just for some information. In exam, these values all will be provided. Okay, latent heat, specific latent heat. I don't want to discuss about latent heat. We straight go to specific latent heat is enough. So specific latent heat, the definition just now we learned. The formula is Q equals to ml. You learned this before, right? In SPM. So Q equals to ml. ml is latent heat of specific latent heat of vaporization or fusion. Okay, so Q is energy. It's the energy, and it's the mass. So unit for latent heat, joule per kilogram. And the amount of energy required to rise 1 kg of substance without change in temperature. So joule per kilogram. Okay, guys. So one example. So how much energy must be supplied to 2 liters of water, 100 degrees Celsius to evaporate it? So 2 liters of water. Okay. So 1 milliliter, we assume like 1 gram. So 1 liter, we take it as 1 kilogram. Okay. Value for water. This is only for H2O. So 2 liter water. So of course the formula must come to your mind is ml. So mass is 2 kilogram. Okay, 2 kilogram. 2 liter is like 2 kilogram. And specific latent heat of fusion, what do you call? Vaporization is used. And you get the final answer, the amount of energy required. So be careful here, the unit megajoule. So final answer is megajoule. Okay, so this is latent heat of vaporization. B, remove from 0.5 kilogram water to freeze it. How much energy must be to remove from 0.5 kilogram water to freeze it? Okay, you want to freeze 0.5 kilogram of water. So use latent heat of fusion. Okay, 0.5 times the latent heat of fusion. So you get this is the amount of energy need to be removed to freeze it. Okay. So melting, freezing, the amount of energy involved is the same, but one is absorbed, another one was like released. So when melting, energy is absorbed, energy need to be supplied. From melting to freezing, energy need to be removed from the substance. Okay. Okay. So this is skip this. It's not it. Okay. So now this is recall back. Okay, recall back how the setup will looks like to find specific latent heat of fusion for ice, specific latent heat of vaporization of water, and specific capacity of aluminum. How does it looks like? The diagram, the setup, you should know. Okay, latent heat of fusion. Okay, let's first we go for specific capacity of aluminum. How does it looks like? the setup. So you need to use a electrical method. Okay, you must use electrical method. So what do you do? Anyone? So you have a, what do you call? You have a cylinder, aluminium cylinder. Then you place what? You use a heater. Then the other side you place a thermometer. Okay, you have a thermometer. Okay, so the heater will give out a certain power. Okay, the power times certain duration, power times time will give you the energy released. And you have some, what do you call? Some insulator surrounding it, right? You have an insulator surrounding it, you have an insulator. Why you need an insulator? Of course, we don't want energy loss to the surrounding. Okay, then how you find specific capacity? The PT equals to MC theta, so you can work out your C, specific heat capacity. Okay, so yeah, so this rough setup, but to be in depth, so of course this could be a setup. Okay, first one, yeah. Okay, so you place a thermometer, you place an immersion heater into a solid block. So you must have what do you call? You must have insulator at the side. Insulator at the side. So this is a setup to find specific capacity for an aluminium. Okay, recall back. Okay, this is specific capacity. The figure 1B is specific capacity for liquid. Okay, this is how the setup should look like. Okay, recall back. What is the difference between solid and liquid? Liquid, you must have a stirrer. You must have a stirrer to continuously stir the water so that to get a uniform temperature. Okay. Here we don't have stirrer for a solid. Okay, so both will have insulator at the side. Okay, both use a heater and both have thermometer. But for solid, when you place a thermometer inside the hole, you must fill it with oil before you place the thermometer. Why? Anyone? Why you need to fill up with oil before we place the thermometer inside the hole? To have a, again, to have a uniform temperature. To have a uniform temperature. Because if you never fill up with oil, only the end part of the thermometer only touch this point at the bottom. So I think the heat, every part of the body is different. So we need to fill up with the water, with the liquid. So we have oil. We have
Wouldn't that technically affect the heat slightly?
heat slightly, yes. The amount of oil we support, we place here is very small oil, little oil. Okay, at the bottom. Yes, slightly, but we put a little, very little oil. Okay, not makes a big difference. Okay. Okay, guys. Now I want to ask you one question, very important one. Okay, the specific capacity obtained during this experiment is overestimated or underestimated than actual value?
Overestimated.
Overestimated. It's always overestimated. Why?
Because heat will always go to the surroundings.
Yeah, some energy lost to the surroundings. Okay, therefore the C calculated will be always overestimated. Okay, remember that in exam they'll ask, is it will be overestimated or underestimated? You have to say always overestimated because some energy of the heater will be lost to the surrounding. Okay, because of course when we calculate PT equals to MC theta. So the C is PT over M theta. Okay. The energy we're going to calculate here, is the energy absorbed by the what do you call, by the solid, by the aluminium, plus the energy lost to the surrounding. Okay, this PT is actually energy calculated, energy absorbed by the aluminium plus the surrounding. But the temperature rise is small. So the PT actually overestimated. Okay, the PT have to be smaller because we don't know how much energy lost to the surrounding. Okay, so therefore C will be overestimated. Okay, it will be overestimated. Okay. Okay, so we go back. So that's the experiment for specific capacity for aluminium. Okay, in exam you must understand how the setup looks like, why you need an insulator, what will happen to the specific capacity, is it overestimated or underestimated, why you need to fill up oil, all you need to explain. Okay. Okay, next, determine the specific Latent of vaporization of fusion of ice, vaporization of water. Okay. So first, let's we go for fusion of ice. How the setup looks like. Anyone? So recall back your Form 5 fusion, Latent of fusion. You have what do you call? You have ice, a filter. Then what do you do? You have what do you call, beaker. So this ice was clamped with the, of course, retort stand. Okay, we have a retort stand here. Then another setup, we'll have what? This setup will put a heater. We'll have a heater inside. We have heater. Then the other setup going to be identically same, but without what? Without heater. Okay, without heater. So first experiment you get M1. The second experiment without heater, but same setup lah. You will get M2. So how do you get your Latent of fusion? PT equals to MLF. So LF is PT over M. Okay, PT times what mass do you use? Anyone? M1 minus M2. Okay, M1 minus M2 to be used. So because we want the mass only melted due to the heater. Okay, M2 is mass melted due to the surrounding. So we only want the mass due to the heater. So M1 minus M2 is used. Find the Latent of fusion. Okay. So this is for the nickel, for the Latent of fusion for ice. Okay. So that is your Latent of fusion of ice, and finally determine the specific Latent of vaporization. Vaporization of water. How it looks like? Try to imagine. Maybe from the, yeah, this setup would be a Latent of vaporization. Okay. So this would be the Latent of beaker A, beaker B, or this can't be Latent of fusion. Immersion heater with ice. Immersion heater with ice, power supply. Second one without heater, because the power supply is not there. Okay, without heater. And this is called Latent of fusion. Okay, filter funnel, immersion heater, and everything. Okay. Okay. So this can go for Latent of vaporization. Okay. So we have a beaker, water, we heat it until the mass M1 is found first. Then after heat it, the mass drop to M2. Then how you measure the specific Latent of vaporization? M1 minus M2, M2 minus M1. In this case, M1 minus M2. M1 minus M2. You get the Latent of vaporization. Okay. So remember this setup. This is the setup for the Latent of vaporization. This is our Latent of fusion, ice, the same amount of ice to be used. And of course, this is your specific heat capacity for solid and liquid. Okay. Okay. So that's about this part. Okay. Before we continue, let's we do some questions first. Okay. The wood file here. Okay. So this is the wood file. So we're done with the specific capacity and specific latent heat of fusion, fusion and vaporization. Okay, so this is the facts to remember. So a lot of things to fill up here. So Q equals to mc theta. Q is what? Heat energy. M is mass of the substance. C is specific heat capacity. Theta is what? Temperature change, change in temperature. Okay, you need to fill up this here. Okay. And heat capacity. So heat capacity of a material defined as heat energy required to increase the temperature of the material 1 Kelvin. What is the unit? Anyone? Heat capacity? Joule per kilogram. Okay. Heat capacity. Remember that. Then heat capacity connected to specific heat capacity by mass times specific capacity is your heat capacity. Okay. As I told you, you can survive without heat capacity. Specific capacity is enough for us to calculate. But sometimes in that question, sometimes they ask you to find heat capacity. Okay, one question. Give a try. 1 minute for you. Get this question. Let me the answer. So an aluminum kettle has a mass of 1.5 kilogram. The specific capacity of the aluminum is 900. Determine the heat capacity. So heat capacity is what? Is mass times the specific capacity. So of course 1.5 kilogram multiplied by 900. So you get how much? 1350 joule per kg. So heat capacity. Next, specific heat capacity of water is 4200. Determine the heat capacity for 2 kilogram of water. So again, heat capacity is mass times specific capacity. So 2 times 4200. So 8400 joule per kilogram. Heat capacity of the water of 2 kilogram. Okay. Next. So look at the third one. If the aluminum kettle is filled with 2 kilogram water and the temperature of the water kettle is rise from 20 degrees Celsius to 100 degrees Celsius, what is the amount of energy required? Aluminum kettle filled with 2 kilogram water. The temperature of the water and the kettle is rise from 20 to 100 degrees Celsius. What is the amount of energy required? So, what is the energy formula? Q equals to, if you want, you can use MC theta if you want, but or we can use heat capacity times changes in temperature, because we already know heat capacity for both of them. So what do you do? So the Q required is C theta of what? C theta of kettle plus C theta of water. Okay, add them, you can get the answer. Okay, so see theta of kettle is what? Kettle is 1350. The temperature change, of course, 100 to 20, so it's 80 plus 8400 for water, the heat capacity for water, times temperature change 80 will give you the energy, amount of energy required, joule. Okay, so if you know heat capacity, just use the heat capacity times the temperature difference, you get the energy. So comment your answer. Comment your answer. So this is the energy required to rise the temperature from 20 to 100 degrees with one assumption. What is the assumption?
No heat is
Is
released,
there
released to the
no
surrounding.
energy loss?
Lost
Yeah,
to
no energy loss. There is no energy loss to the surrounding. This is the energy required to rise the temperature of the kettle and the water from 20 to 100. Okay. Okay, so this is a warm-up question, how heat capacity and specific capacity is linked. Okay. Okay. So the experiment measurement of specific capacity for solid and liquid, just now I'll show you the diagram, how it looks like. Okay. You can get it from the Google. Okay. And you learned this before, so recall back. Okay, next. Example 2. 1 minute for you. Give a try. Okay, this is like an air dryer. So air dryer. A steady stream of air is drawn into the tube with a power of 500 watts. The density of the air is 1.2 kg per meter cube. Specific heat capacity of the water is of what? Of the air is 1000 joule per kg per Kelvin. Calculate the maximum temperature rise of the air for a flow rate of 0.4 meter cube per second. Or the air drawn from the air dryer, the air drawn and move in. The amount of water leave the air dryer is about 0.4 meter cube of air every second. Okay. Now this volume per over time value, V over T. So calculate the maximum temperature rise. Question asking, what is the change in temperature? Power given. So how do you start your working with? What type of energy equal to what type of energy? The electrical energy should be equal to heat energy. So PT equals to, of course, MC, change in temperature. So you have to start with this. Please calculate the changes in temperature. So anyone get the temperature value? You know power, but time not given. Time not given. The amount of mass of the air not given. Specific capacity is given, and this is all given. You need to find the mass and the time by using this volume per unit time. The volume, the amount of volume of gas leaves, and the density. Yes. With the density and the volume per unit time, I think you can find the mass and time. That's the trick part here. How you can bring density in this formula? If you can do that, you can find the answer. How you can bring density in this formula? The mass, right? How to change mass to density? So density, what is mass? Density times
Volume.
volume. It's your mass. Okay, so now I think you can get the answer, right? So make C as the subject. C as a subject, what do you get? PT over rho B, PT over, sorry, not C. So you want the changes of theta, right? Changes of theta. PT over rho B C. Okay. But you are given volume per unit time. You are given volume per unit time. So here time over volume. Maybe you can written this formula like this: rho volume per unit time times C. Correct? The time we can bring it down, but it's going to be volume over time. Volume over time.
Yes.
So this is your changes in temperature. This is your changes in temperature. So what's the answer you got? So changes in temperature is what? The pressure, power 500, and density is what? 1.2, and the volume per unit time the air passes through is 0.4, and C specific capacity is found to be 1000. So whatever answer you got, this is the change in temperature in Kelvin. So what's the answer you got? Yep, 0.
One
Anyone?
04.
104. 1.04.
Yes.
1.04. Okay, 1.04 Kelvin.
Yes.
So yeah. So this is how the working should be. Okay, class. So this is something different way of asking questions. Air is flowing inside. They give a volume per unit time value. So still PT equals to MC theta, but the mass have to convert to density times volume, and the volume and time have to pack together because they give volume over time value. Volume per unit time 0.4 is given, so you have to pack the V over T together to substitute as 0.4. Okay, that's the thing. Okay, so guys, so this is today's lesson for this session. So I see you at 10 o'clock later. Okay, today extra class I think at 5 o'clock, right? It's going to be quite hectic because today you have twice physics. So what I plan is, can we have it next Friday, because your official schedule was ending on Thursday, right?
Yeah.
Okay. So maybe Friday we can have at 10 o'clock lah. Just it won't be very hectic for you. Okay. So today we have two sessions only. So next week Friday we have it another one 10 o'clock. Okay. Yes. Any questions? Okay. So later 10 o'clock we'll be continue doing this question, and we do more questions to strengthen this idea. Okay. Okay. So if no questions, we stop here. So see you back at 10 o'clock.